All right, this is the last three problems for this section, 57, 59, and really there's more than that. There's five altogether, 57, 59, 61, 71, and 72. If we look at number 57, it says two wave pulses on a string approach one another at time t equals 0, as shown in the figure below. Each pulse moves with a speed of 1. Make a careful sketch of the resultant at the times t equals 1, 2, 3, and 4. Assume that superposition. So remember, when they come together, if they're both going up, they're going to add together. To see this solution, what I did is I went ahead and scanned in the actual key. Makes it a little bit easier to see. So when you look at the sketches of what they've done, at t equals 1 second, all they've done is they've just moved over just 1 meter. And so you'll see that they're a little bit closer than they were originally. Originally is up in the corner here. At t equals 2 seconds, they've both moved over again, and you'll notice that we've lost the up and down area that is at the beginning of this pulse and at the beginning of this pulse. And beginning, by that I just mean where the front of the arrow is. So that's gone. In the next second, which would be at 2.5 seconds, you'll see that the two pulses overlap. And when they do that, we've gone from a height, we just call this h, to double that height. And it's because the two pulses added. At 3 seconds, you'll notice that it looks just like it did at 2 because the pulses are now going to separate. And then at 4 seconds, you'll see that they've totally separated. So that's basically how to do this. I have seen these on the AP test. They're typically not this easy, but they are very manageable and they're pretty easy points to get. This is one that's a little bit more like what you would see on an AP test because they are different shapes. So you have more of a square shape and more of a triangle shape. And once again, they're moving towards each other. When they get right up next to each other, you'll see they kind of make this kind of box, apartment, and house shape, I guess is the best I could say. But when they combine, you'll see that you get the box, and because this builds on top of the box, this kind of roof shape, you'll see you almost could draw a house if you wanted to out of that. So here we just put a little door on the front, put some windows in it. Um, but that's essentially what you see. You wouldn't want to draw the doors and the windows. They'd probably take points off or chuckle at you, depending on who's grading it. And then when they separate, same thing. You'll notice that this one and this one are opposites. And finally, at that last time of 4 seconds, you'll see that they're now just moving in their independent ways. So that would be number 57 and number 59. The next question that we have is number 61. And for number 61, the problem states you've got a pair of in-phase stereo speakers. They're placed side by side, 0.85 meters apart. You stand directly in front of one of the speakers, 1.1 meters from the speaker. What is the lowest frequency that will produce constructive interference? So that's where the two waves are moving, okay? And when they move, they are in phase. So that means that as the top one is moving up, so is the bottom one. So when you get them together, their amplitude is much higher. And when their amplitude is much higher, then that's much louder. So just like an amp that you would use to amplify a guitar, this is the same thing. We're just making the wave very big. And so at this point, what we need to do is we've got the two speakers, and they've drawn this picture here. They are 0.85 meters apart, and you are standing 1.1 meters, okay, and you're right in front of one of the speakers. You're right there. So now we can draw this triangle, and we want to find this distance D. This distance D will show where they both will have the sound waves that are coming out, and those sound waves will then overlap at the point where they hit you. So we want to know what that distance is from the speaker. To find that distance, we say D is equal to the square root of, now we've got 0.85 and 1.1, so we're going to do 0.85 squared, put that point back in there, plus 1.1 squared. I like to put those in parentheses, makes it easier to see. And that should be equal to 1.39 meters. We know that the wavelength is equal to the change in the distance. So what we'll do is we're going to say 1.39 is our distance here. And we need to subtract off of that the distance we are from the speaker. So we get 0.29 meters. So that should be the wavelength that we're looking for. Um, Now at this point we can just say that frequency is equal to the speed of sound divided by the wavelength. And we know that the speed of sound is 343 meters per second. The wavelength we just determined to be 0.29 meters. And so that would give us 1.2 kilohertz. So that's really 1,200 hertz. So you'll probably find this answer first, and then if you need to, you can transfer it into kilohertz. Probably on mastering, it asks you to take that and use the unit of a kilohertz. For number 60, for number 71, it says the human ear canal is much like an organ pipe. So now we're looking at open and closed end pipes. It is closed at one end, which means that it is open on the other. So that's the key. So this is a one end is closed while the other end is open. So if we think about your ear canal going up to your eardrum, so this is where your eardrum would be. This is the hole in your ear where sound goes in, and then it goes in and hits your eardrum. There's the distance between the two is about 2.4 centimeters or 0.024 meters. So it's a little bit of a distance. Because this is a pipe closed at one end, we need to use the equation. The frequency, the fundamental frequency, is equal to N times V all over 4L. And that's because, remember, the frequency is equal to the speed of sound divided by 4 times the length because of the way that this produces sound waves. And we've talked about that in class a little bit. So if we want to find out what this frequency is, all we have to do is plug all our numbers in. Because it says fundamental, our N value is 1. That's what fundamental means. We know the speed of sound here is about 343 meters per second, and we're going to do 4 times the length of our pipe, and the length of our pipe is 0.024 meters. So we end up with a frequency of 3.6 kilohertz, or 3,600 hertz, which is going to be about the same thing. The wavelength on this one then is going to be equal to 4L over N. We said because it's a closed-end pipe, that's the equation you use. So we're going to say 4 times 2.4 centimeters, and then we can divide that by 1 because that's our N. And that gives us 9.6 centimeters for the wavelength. So that's the fundamental frequency and the wavelength. When it says the second harmonic, the only thing you need to change here is we know the fundamental frequency N is equal to 1 is fundamental. N equals 2 would be the, that would be the first harmonic. And if N is equal to 3, that is what we call the second harmonic. So it's 2 octaves higher. If you know music, you'll understand what I mean. And if you don't, that's okay. You just need to memorize that the fundamental is N equals 1 and N equals 2 is the first harmonic, N equals 3 is the second. So whatever you have, you just add 1 to it. And so we can go through and find this. So we can say F3, so that would be the second harmonic where N equals 3. So we usually illustrate that as F3 is equal to NV all over 4L. So we plug our numbers in. This time it's 3 times 343, and we divide that by 4 times 0.024. And when you're done, you should end up with a fundamental frequency here of 11 kilohertz. So 11 kilohertz. If we take that 3.6 that we originally had, if we take the 3.6 we originally had and we just multiply that times 3, you'll notice that we'll get approximately the same answer. So that's really what you could do here. That'd be a little bit quicker on the AP test. Finally, to find the wavelength of that third harmonic, that would be equal to 4 times the length again, all over the number of nodes. That's what the N stands for. And then that would be equal to 4 times 2.4 centimeters. And then we can divide that by 3. And your wavelength here now is 3.2 centimeters. So it's a little bit shorter, which means that the frequency is going to be higher. And that's number 71. The last one that we have is this one. This is the last part of number 71, and it says suppose a person has an ear canal that is shorter than 2.4 centimeters. Is the fundamental frequency of that person's ear canal greater than, less than, or the same as the value found in part A? And it should be greater. Okay, and they always say explain, just like they do on the AP test. The fundamental frequency is inversely proportional to the length of the ear canal. So the fundamental frequency, remember we said, is NV over 2 or 4L. So for what we're doing, we look at 4L. And because these are inversely related, if the ear canal is shorter, so if this number goes down, okay, then our fundamental frequency's got to go up. And that's the difference between the two. Finally, the last one is you have a guitar string which is 66 centimeters long, vibrates with a standing wave that has 3 antinodes. And we've talked a little bit about what nodes and antinodes are. So if you have a standing wave, and that standing wave kind of looks like this one has, let's see, has two, let's see, has there we go. Let's draw this. This one has 3 antinodes. So there's 2 antinodes and 3 antinodes, and you always add 1 to show the number of nodes that you have. So here's 1, 2, 3, 4 nodes. They want to know what harmonic is this. And so when we answer this one, because the number of antinodes and the harmonic go together, we say that this is the third harmonic. And they want to find out what is the wavelength of this one. So the third harmonic would be equal to 2L over N. And so that's 2 times the 66 centimeters. And because our N number, our number of antinodes is 3, we just plug that number in. Do your math, you should get 44 centimeters. And that is the end of the sound superposition and some of the other problems here that we have for standing waves.